Welcome back to our deep dive series. Especially for you number theory students out there, today we're jumping into a really fascinating sequence from the OEIS.
Ah, yes, the online encyclopedia of integer sequences. Which one is it today?
It's A000284. It's often called the cubed recurrence sequence.
Right. That one's a classic example, isn't it?
It really is. Our mission, sort of, is to figure out how such, well, simple-looking rules can make numbers just explode. So let's unpack this one.
Yeah, what's so captivating, I think, is how you start with something that looks completely manageable, basic even, but it generates terms that grow incredibly fast. It really demonstrates that hidden power in recurrence relations.
It's like, that snowball analogy.
Mm.
But this one doesn't just grow. It sort of compounds on itself with that cubing effect. It just accelerates like crazy.
Precisely. It's a great illustration of nonlinear dynamics in a purely numerical setting.
Okay, so let's get the snowball rolling. How is A000284 actually defined?
It's built on a recurrence relation, specifically an equals an1 cubed
Cubed.
plus an2.
Got it. So an13 plus an2. And where does it start? What are the initial conditions?
They're very simple. A0 is 0 and A1 is 1.
0 and 1, okay.
And it's really that interaction, the an1 being cubed, that drives the whole thing. It's not just adding the previous term. It's adding the cube of the previous term. That makes a huge difference compared to, say, Fibonacci.
Right, that nonlinear part is key. So let's walk through the first few terms just to see this cubing effect really kick in.
Sure.
We have a 0, 0, A1, A1. So A2 would be A13 plus A0. That's 13 plus 0, which is just 1.
Still seems pretty tame at this point.
Yeah, exactly. Then A3, that's A2, 3 plus A1. So 13 plus 1, which gives us 2.
Okay, it's a slight increase,
Still manageable. Now A4, that's A3, 3 plus A2. So 23 plus 1.
which is A plus 1, so 9.
Right, 9. Okay, starting to move a bit. But now A5, that's a 4, 3 plus A.
And our 4 was 9, so we need 93.
93 is 729.
Right, 729, plus A3, which was 2.
So it's 729 plus 2. That's 731.
And there's the jump.
Wow. Okay, from 9 to 731 in one step.
Exactly. You can feel that acceleration starting. And if you go just a couple more steps, I mean, '06 is already enormous, like 700, 313 plus 9. That's hundreds of millions.
Hundreds of millions, just for a 6.
And a 7 is just astronomical, quintillions, I think. It goes from these tiny single digits to numbers that are hard to even write down incredibly quickly, all because of that cube.
That really hits home the snowball analogy, doesn't it? It's just mind-boggling growth. Now, I saw there's also an alternative formula mentioned for N0, something like AN is approximately floor, C3N.
Ah, yes. That's a fascinating aspect.
What's the deal with that C and the 3N in the exponent?
Well, C is a constant, roughly 1.0275. And that formula, C raised to the power of 3 raised to the power of n, shows the structure of the growth. It's not just exponential. It's what we call hyperexponential, a tower of powers.
Tower of powers.
Right, tells you the growth is much faster than something like 2n. It's useful because it gives you a very good estimate of how big these terms get without calculating all the intermediate ones.
That makes sense. So for anyone listening who likes coding, how would you, get your hands dirty and compute this sequence?
Oh, it's pretty straightforward to implement, actually. You can use recursion with memoization, basically telling the function to remember values it's already calculated.
Right, so you don't recompute things.
Exactly. Or just a simple iterative loop works fine, too. The main challenge isn't the logic. It's handling the numbers themselves. They get so big so fast, you'll quickly need libraries that can handle arbitrary-precision integers. Standard 64-bit integers won't cut it for very long.
Good point. A practical challenge there. And just to place it in context, back in the OEIS database, this sequence, A000284, it was contributed by Stephen J. Greenfield. And it's tagged as non-negative. And interestingly, easy.
Well, easy in the sense that the definition is simple to state and understand. The consequences of that definition, the growth, are anything but trivial.
That's a great way to put it. So wrapping this up, what's the big takeaway for you, the learner, from this deep dive into A000284?
I think it's a fantastic aha moment. It shows vividly how a simple nonlinear rule, that cubing operation, can lead to absolutely explosive complexity. It's a reminder that profound behavior can emerge from very simple systems.
Yeah, it really demonstrates that hidden power, even in something labeled easy.
And it makes you wonder, doesn't it? How do these kinds of super fast-growing sequences relate to other areas? Maybe in modeling phenomena where things suddenly take off, like certain chemical reactions, maybe even some social dynamics.
Or perhaps aspects of chaos theory. where small changes have huge effects.
Precisely. It opens up questions about predictability when even slight nonlinearities are present. How can a definition so basic lead to values so immense?
Definitely something interesting to chew on as you continue your own explorations in the, well, the amazing world of numbers.